In this lecture, we will talk about measuring the voltage and current using the voltmeter and ammeter, the delta-to-Wye or pi to T equivalent circuit, and we will solve some problems. An ammeter is an instrument designed to measure the current. In order to measure the current in a branch, you need to cut the circuit and place the ammeter in series with the circuit element whose current is being measured. A voltmeter is an instrument designed to measure the voltage. The voltmeter is placed in parallel with the circuit element whose voltage is being measured. An ideal ammeter or voltmeter has no effect on the circuit variable it is designed to measure. That is, an ideal ammeter has an equivalent resistance of 0 ohms and functions as a short circuit in series with the element whose current is being measured. An ideal voltmeter has an infinite equivalent resistance and thus functions as an open circuit in parallel with the element whose voltage is being measured. The configuration for an ammeter used to measure the current in R1 and R2 is shown in the figure to the left. As shown in the figure, the branch where R1 is placed is cut and an ammeter is placed in series with R1. The same thing for R2, the branch is cut and an ammeter is placed in series with R2. The figure on the right illustrates the configuration for a voltmeter used to measure the voltage across R1 and R2. As shown, a voltmeter is placed in parallel with R1 and another voltmeter is placed in parallel with R2. Resistors RA, RB, and RC in the circuit shown are referred to as a delta interconnection because the interconnection looks like the Greek letter delta. It is also referred to as the pi interconnection because the delta can be shaped into a pi without disturbing the electrical equivalence of the two configurations. Resistors R1, R2, and R3 in the circuit shown are referred to as a Y interconnection because the interconnection looks like the letter Y. The Y configuration is also referred to as a T interconnection because the Y structure can be shaped into the T structure without disturbing their electrical equivalence. In order to simplify circuit analysis, we sometimes need to transform a delta configuration into a Y configuration and vice versa. In order to do this, we notice that the equivalent resistance between nodes A and B in the delta configuration is equal to RC in parallel with RB plus RA, which is equal to R1 plus R2 in the Y configuration. This is given by equation 1. In the same approach, the equivalent resistance between nodes B and C in the delta configuration is equal to RA in parallel with RC plus RB, which is equal to R2 plus R3 in the Y configuration. This is equation 2. The equivalent resistance between nodes C and A in the delta configuration is equal to RB in parallel with RA plus RC and is equal to R1 plus R3 in the Y configuration, and this is given in equation 3. Adding equations 1 and 3 and subtracting equation 2 yields R1 plus R2 plus R1 plus R3 minus R2 minus R3 equals to RC times RA plus RB plus RB times RC plus RA minus RA times RB plus RC over RA plus RB plus RC, from which we get R1 equals to RC times RB over RA plus RB plus RC. The same approach can be used to find R2 and R3 in the Y configuration in terms of RA, RB, and RC in the delta configuration. In order to transform a delta configuration to a Y configuration, notice that each resistor in the Y configuration is equal to the multiplication of the two delta resistors connected to the same node over the summation of all the resistors. That is, R1 equals to RB times RC over RA plus RB plus RC. R2 equals RC times RA over RA plus RB plus RC, and R3 equals RA times RB over RA plus RB plus RC. In order to transform a Y configuration to a delta configuration, you should keep in mind that each resistor in the delta configuration is equal to the sum of the product of all the resistors in the Y configuration over the resistor that is not connected to the two nodes. That is, RA equals to R1 times R2 plus R2 times R3 plus R3 times R1 over R1. RB equals to R1 times R2 plus R2 times R3 plus R3 times R1 over R2. And RC equals to R1 times R2 plus R2 times R3 plus R3 times R1 over R3. It is very important to understand that transforming between delta to Y or Y to delta configurations does not affect the voltages between nodes A, B, and C, or the current flowing in these nodes. For example, the current I1 flowing in node A in the delta configuration is equal to the current I1 flowing in node A in the Y configuration. This is also true for the current I2 flowing in node B in both configurations, and for current I3 flowing in node C in both configurations. Also, the voltage between node A and C, VAC, in the delta configuration is equal to voltage VAC in the Y configuration. This is also true for VAB and VBC. This figure illustrates how a Y to delta transformation can be used in order to simplify circuit analysis. Let's say that we wanted to find the equivalent resistance between nodes A and C. We can do that by transforming the Y configuration consisting from R1 plus R2 and R3 to a delta configuration consisting from RA, RB, and RC, from which we notice that the equivalent resistance between nodes A and C is equal to the parallel resistance of RA and R4 in series with the parallel resistance of RC and R5, and this total resistance is in parallel with RB. These two figures illustrate how a delta-to-Y transformation can be used in order to simplify circuit analysis. To find the equivalent resistance between nodes A and C, we need to transform the delta configuration of RB, RD, and RC into a Y configuration of R3, R4, and R5, from which the equivalent resistance between nodes A and C is equal to R1 plus R3 in parallel with R4 plus R2 in series with R5. In this example, we need to find the current and power supplied by the voltage source. In order to find the current supplied by the voltage source, we need to find the equivalent resistance between nodes A and D. This can be easily done after replacing the upper delta configuration or the lower delta configuration by its equivalent Y configuration. Transforming the upper delta to Y yields R2 equals to RA times RC over RA plus RB plus RC equals to 50 ohms. R3 equals to RA times RB over RA plus RB plus RC equals to 10 ohms, and R5 equals to RB times RC over RA plus RB plus RC equals to 12.5 ohms. The total equivalent resistance can easily be found by noting that R1 is in series with R2, which in turn is in series with the parallel combination of R3 in series with R4 in parallel with R6 in series with R5, which equals to 80 ohms, from which the current supplied by the voltage source I equals to 40 volts over R equivalent, which equals to 0.5 amps. The total power dissipated by the voltage source is equal to I squared times R equivalent equals to 20 watts. In problem 1, we need to find the power dissipated in R5. In order to find the power, we need to find the current flowing through R5. By transforming the upper delta to Y, we get RA equals to R2 times R4 over R2 plus R4 plus R6 equals to 6 ohms. RB equals to R2 times R6 over R2 plus R4 plus R6 equals to 10 ohms. And RC equals to R4 times R6 over R2 plus R4 plus R6, which equals to 15 ohms. The total resistance as seen by the voltage source is given by R1 in series with RA, which is in series with the parallel combination of RB in series with R3 in parallel with R5 in series with RC, which equals to 20 ohms. The current supplied by the voltage source I equals to V over the total resistance equals to 15 amps. In order to find the current flowing in R5, we need to find the voltage between nodes E and D, where VED equals to I times the equivalent resistance between nodes E and D, which is given by RB in series with R3 in parallel with R5 in series with RC, from which VED equals to 144 volts. The current flowing through R5, IR5 equals to VED over RC plus R5 equals to 6 amps, from which the power dissipated in R5 equals to I R5 squared times R5 equals to 324 watts. In problem 2, we need to use the delta-to-Y transformation in order to find I0. Transforming the upper delta to Y yields RA equals to R2 times R4 over R2 plus R4 plus R6 equals to 6 ohms. RB equals to R2 times R6 over R2 plus R4 plus R6 equals to 10 ohms. And RC equals to R4 times R6 over R2 plus R4 plus R6 equals to 15 ohms, from which we can obtain the total resistance as seen by the voltage source, which is given by R1 in series with RA, which is in series with the parallel combination of RB in series with R3 and parallel with R5 in series with RC, which equals to 25 ohms. The current supplied by the voltage source I equals to V over the total resistance equals to 20 amps. The voltage difference between nodes E and D equals to the current I times the equivalent resistance between nodes E and D, which is given by the parallel combination of RB in series with R3 and parallel with R5 in series with RC, from which VED equals to 336 volts. I1 equals to VED over RC plus R5. I2 equals to VED over RB plus R3. In order to find the voltage difference between nodes B and C, we chose node D as the reference node, from which VBC equals to VBD minus VCD, which equals to I2 times R3 minus I1 times R5 equals to 150 volts. It is very important to understand that the voltage difference between nodes B and C in the Y configuration is the same voltage difference between nodes B and C in the delta configuration. From the original figure of the problem, we find that I0 equals to VBC over R6 equals to 3 amps. In problem 3, we need to find I0 and the power dissipated in R8. In order to simplify the analysis, we rearrange the resistors in the previous circuit to obtain the circuit shown here. Please note that in the previous circuit, R equivalent is equal to R4 plus R5 times R7 over R4 plus R5 plus R7 equals to 16 ohms. Transforming the upper delta to Y, we get RA equals to R1 times R6 over R1 plus R6 plus R8 equals to 4.9 ohms. RB equals to R1 times R8 over R1 plus R6 plus R8 equals to 2.4 ohms. and RC equals to R6 times R8 over R1 plus R6 plus R8 equals to 18.4 ohms. The total resistance as seen by the voltage source is given by RA in series with the parallel combination of RC in parallel with R equivalent in series with R5 in series with RB in series with R3, from which the total resistance is equal to 20 ohms. The current supplied by the voltage source I equals to V over the total resistance equals to 12 amps. Applying KVL on the loop yields minus 240 plus I times RA plus VEC plus I times R3 equals to 0, from which the voltage difference between nodes E and C, VEC, equals to 121.2 volts, from which I2 equals to VEC over RB plus R2 plus R equivalent equals to 5.4 amps. The voltage difference between nodes A and B, VAB, equals to IRA plus I2RB equals to 71.76 volts. This is also the voltage difference between nodes A and B in the delta configuration of the original circuit, from which I0 equals to VAB over R1 equals to 8.97 amps. The voltage difference between nodes B and C, VBC, equals to I2 times R equivalent plus R2 equals to 108 volts. This is also the voltage difference between nodes B and C in the delta configuration in the original circuit, from which the power dissipated in R8 equals to VBC squared over R8 equals to 388.8 watts. In problem 4, we need to find I2, I1, V1, and the power dissipated by the voltage source. By transforming the left side delta to Y, we obtain the simplified circuit shown here. In the previous figure, RA equals to R2 times R5 over R2 plus R4 plus R5 equals to 6.72 ohms. RB equals to R2 times R4 over R2 plus R4 plus R5 equals to 17.36 ohms, and RC equals to R4 times R5 over R2 plus R4 plus R5 equals to 29.76 ohms. The total resistance as seen by the voltage source is given by R total equals to R1 in series with RA in series with the parallel combination of RB in series with R3 in parallel with RC in series with R6 in series with R7, which equals to 45 ohms. The current supplied by the voltage source I equals to V over the total resistance equals to 12 amps. The voltage difference between nodes E and F, VEF, equals to I times RB in series with R3 in parallel with RC in series with R6 equals to 240 volts. from which I2 equals to VEF over RC plus R6 equals to 4 amps. I3 equals to VEF over RB plus R3 equals to 8 amps, from which the voltage difference between nodes A and B is given by VAB equals to I times RA plus I3 times RB equals to 219.52 volts. This is the voltage difference between nodes A and B in the delta configuration, from which I1 equals to VAB over R2 equals to 7.84 amps. The voltage difference between nodes B and C, VBC equals to VBE minus VCE, which equals to minus I3 times RB minus I2 times RC, which equals to minus 19.84 volts equals to V1. The current flowing in the direction of the voltage rise and the voltage source, from which the power equation is written as P equals to minus IV equals to minus 6.48 kilowatts. Since the power is negative, it is delivered. So the delivered power equals to 6.48 kilowatts.